Hi everyone, I'm Dan Fullerton, and today I want to talk to you about basic circuit analysis. Our objectives are going to be to analyze a circuit consisting of series and parallel resistors, just resistive circuits with power supplies, and apply Ohm's law and Kirchhoff's rules to DC circuit analysis. So, electric circuits are closed-loop paths through which current can flow, and conventional current always flows from high to low potential. However, in most circuits, the charge carrier is actually an electron, a negative charge, so the electrons actually flow in the direction opposite conventional current, or from low to high potential. Now, as we talk about circuits, we're building three-dimensional structures, and we need to model them in a way that's convenient. So oftentimes we use circuit schematics, which are 2D representations of the 3D circuit. The symbols that represent the circuit elements, while lines represent the wires. Now, for current to flow, we need a source of potential difference, such as a battery or a cell. And note that current only flows in a complete path. If you open up the path at any point, current stops flowing. So, some of our circuit symbols, we've got a cell. Cells connected together gives you a battery, a switch, a voltmeter and an ammeter, which we'll talk about in another video, resistor, a variable resistor, and finally a lamp, which is basically a resistor that gives off light. So, as we talk about series circuits have only a single current path. If you remove any element, you get an open circuit. So a series circuit would typically look something like this. Maybe a battery and a couple of resistors. Only one path for current to flow. And as we look at series circuits, if we have resistors that are in series, it's oftentimes useful to replace them with an equivalent resistor. A one resistor that takes the place of those three resistors, or gives you the equivalent resistance. To find the equivalent resistance for resistors in series, all we have to do is add up the values of resistance of each of the resistors in series. So the equivalent resistance for resistors in series is going to be, well, if that's R1 and we call that R2 and that's R3, then our equivalent resistance will be R1 plus R2 plus R3. And you do that for however many resistors you happen to have in series. If we look at parallel circuits, on the other hand, parallel circuits have multiple current paths. Removing a circuit element may allow other branches of the circuit to continue operating. So a parallel circuit might look something like this. We'll put a battery in here again, and now we'll put a resistor here, and a resistor here, and a resistor here. Now we have multiple current paths. Current can flow this way, it can flow that way, it can flow that way, multiple paths. And if we remove any single element here, for example, if we get rid of that middle resistor, we can still have current flow through that resistor and that resistor. We haven't completely disabled our circuit. Now, just like we did with series circuits, at times it's useful to replace resistors that are in parallel with an equivalent resistance. The equivalent resistance for resistors in parallel can be found by taking 1 over the equivalent resistance is equal to 1 over R1 plus 1 over R2 plus 1 over R3, and so on for as many resistors as you happen to have. And a nice little shortcut, if you only have 2 resistors in parallel, then R equivalent is equal to R1 times R2 over R1 plus R2. Can save you a little bit of time. Now, as we talk about some of the tools to help us analyze circuits, one of these very useful tools is called Kirchhoff's current law, or KCL, sometimes called the junction rule. It says the sum of all current entering any point in a circuit must equal the sum of all the current leaving that point in the circuit. It's really a restatement of the conservation of charge. So in the diagram below, this represents currents in a segment of an electric circuit. If we want to know the current flowing through this ammeter A, well, we have 2 and 3 amps coming in, so 5 amps in, and we have 4, 5, 6, 7 coming out. That means that we must have another 2 amps coming in for everything to balance. What comes in must come out. Law of conservation of charge. Another useful tool is Kirchhoff's voltage law, KVL, sometimes called the loop rule. What it says is that the sum of all potential drops in any loop of a circuit must be equal to 0. As you go around any circuit, starting from one point, go all the way around back to that same point, the sum of all the potential drops must be 0. It's a restatement of the law of conservation of energy. And the way this works is if I were going to draw this as a battery, I would probably draw something like this. Let's make R1 and R2 here and have this come back. We'll call this VB. That's the negative side. And as we go through here, if we have some current I, then we'll have a voltage drop plus minus here. Let's call that V1. And here, that voltage drop we'll call V2. Kirchhoff's voltage law, KVL, says if we start at any point here in the circuit, let's start right down here, for example. As we make a loop, the first thing we come to is negative VB. So minus VB. As we keep going, I see the plus V1. And I go a little further, I see the plus V2. And I come back to where I start. That must equal 0. Any loop around the entire circuit must have a potential, must sum all the potential drops to 0. Kirchhoff's voltage law. Now, as we analyze some of these circuits, what's oftentimes useful for analyzing the circuits is known as a VIRP table. VIRP, standing for voltage, current, resistance, and power. If we put that together for all the elements in a circuit, it can oftentimes give us a nice insight into how the entire circuit works. And we'll show that and demonstrate it over the next few examples. What we're really doing is using a combination of Ohm's law, KCL, KVL, in the tables to organize our information and our understanding to solve for unknown elements of these given circuits. So let's take a look here at our basic series circuit analysis. Here we have a 12-volt battery, a 2 kilo ohm resistor, a 2 kilo ohm resistor, and another 2 kilo ohm resistor. So I'm going to label these R1, R2, and R3, and then I'm going to make my VIRP table. I'll list the elements in our circuit down the left-hand side, R1, R2, R3, and I'll make a row for the total. Across the top, V, I, R, P, where all of my values have to be in SI units. I'll make a table here, and then we'll start to fill in what we know. All right. R1, R2, and R3, we know each of those is 2,000 because they're 2 kilo ohms. And we put this in SI units, so in ohms. We also know the total voltage provided by the source of potential difference is 12 volts. Well, as I look at this, it's pretty obvious to see I can find the equivalent resistance, or the resistance of the entire circuit, by adding up my 3 resistors in series. So I get a total resistance of 6,000 ohms. Well, now that I know 2 things in any row, I can always solve for the other 2. If I want the current, I, that's just V over R by Ohm's law. That's going to be 0.002 amps. So I must have 0.002 amps going through that element. But because it's a series circuit, whatever enters any element must leave that element. We only have one path. All of my currents must be 0.002. Now I know 2 items in all of these rows. I can solve for all of the others. If I take a look here, if I know I and R, I can find V using Ohm's law. V equals IR. That's going to be 4 volts, 4 volts, 4 volts. And that makes sense. If we have 12 volts here, negative 12, as we go this direction, we must drop 4 here, drop 4 here, drop 4 here to get back to 0. And the drops should all be the same since we have the same amount of resistance. And they are 4, 4, and 4 to give us our 12. We could also find the power pretty easily with a variety of formulas. V times I, or I squared R, or V squared over R. It'll give us the same thing for regardless of how we calculate it. So the power dissipated by resistor R1, V times I, 4 times 0.002, or 0.008 watts, 8 milliwatts. Power dissipated by R2 the same, by R3 the same. And to find the total power, we could take V times I for the total, or add up the individual powers dissipated to come up with 0.024 watts, or 24 milliwatts. Using a VIRP table and what we know about Ohm's law and series circuits to fill in our unknowns. If we take this a little bit further, let's do this with the parallel circuit analysis. Same idea. Let's make our VIRP table to begin with. Let's call this R1, R2, and R3. So our VERP table will have R1, R2, R3, and our total, and V, I, R, and P. Now as we make our table here, we'll begin to fill in what we know. Each of our resistors again is 2,000 ohms. Our total voltage is 12 volts again. And because it's a parallel circuit, it's easy to see that across each of these resistors we must drop all 12 volts. So the voltage drops are going to be the same in a parallel circuit. Well, now we know two things in these rows. We can solve for the current. I equals V over R. That's going to be 12 over 2,000, or 0.006 amps, 6 milliamps. Same for R2. Same for R3. And it should be pretty easy to see that if we have 0.006 here, and 0.006 here, and 0.006 here, that the total, we must add all those currents up to come up with the total current of 0.018 amps, or 18 milliamps. Well, now we can find the total resistance, R equals V over I by Ohm's law, which is going to be right around 667 ohms. Or we could have found that by using our equivalent resistance for a parallel series circuit configuration formula. Well, now the power again should be pretty straightforward. Just multiply V times I for all of these, and I come up with 0.072, 0.072, 0.072, and add them up, or V times I down here, to come up with the total power dissipated of 0.216 watts, or 216 milliwatts. But what happens if a circuit isn't completely serial or parallel? And that happens quite regularly. Well, look for portions of the circuit with parallel elements and see if you can't combine them into an equivalent element that's in series. Then analyze it with a VERP table and work your way back using KCL and KVL until you know the current, voltage, and resistance of each of those circuit elements. Let's take a look. Here we have a circuit that has series and parallel elements in it. And the first thing I'm going to do here is I notice I have two resistors, R2 and R3, over here that are in a parallel configuration. So what I'm going to do is I am going to replace them with an equivalent resistor in an equivalent circuit. So this will be equivalent to, I'll put a 10 volt battery over here, plus minus 10 volts. I still have R1, 20 ohms. I'm going to replace R2 and R3 with what I'm going to call R23. And the equivalent resistance for 30 and 50 in parallel, well, I can use that formula, R2, R3 over R2 plus R3. So that's 30 times 50 over 30 plus 50, which is about 18.75 ohms. That's the equivalent. And then we'll come back and we've still got R4 down here of 20 ohms. Well, now it's pretty easy to see if this is just a basic series circuit. I can find the current flowing through the circuit. That's just going to be the total voltage divided by the total resistance. Or if I equals V over R, that's going to be 10 volts over 20 plus 20 is 40 plus 18.75 over 58.75 ohms, which will give me a current of about 0.170 amps. Great, so let's fill that in with my VERP table. I have here R1, R2, R3, and R4. And as I do that, over the top we'll put our V, I, R, and P. Now, R1, 20. R2 30, R3 50, and R4 20. I also have my total down here. There we go. And as I do this now, let's see what we can fill in to make this all work out nice and pretty. Let's see, our total voltage must be 10. We know that our current, our total current, must be 0.170 amps. So here I must have 0.17, and here I must have 0.17, so I'll fill that in through R1 and R4. Well, I can now find the voltage drop across R1 and R4 using Ohm's law, V equals IR. That's going to be 3.4 volts here, 3.4 volts here. That means that these two in parallel must share the same voltage drop. 10 minus 6.8 leaves them 3.2 volts to drop across each of those. So now I can find the current through each one of those. I equals V over R. 3.2 over 30 is going to give me a current of about 0.107 amps here. And 3.2 over 50 is going to be about 0.064. And adding that up with rounding error comes up to 0.17, so KCL still holds. My total resistance, R equals V over I, 10 over 0.17, is about 58.75, the same thing we found over here. And now we can also fill in our powers. V times I will be about 0.578 watts, 0.341 watts, 0.205 watts, and 0.578 watts. And add all those up, or V times I here, 10 times 0.17, will give us 1.7 watts for the total power dissipated by the circuit. Let's take a look at one more. Here we're looking at a problem with two voltage sources. We've got a 12-volt supply here and a 16-volt supply here. That's going to make things a little bit more complicated, but still certainly doable. So let's start out by defining a couple items. Let's call the current through R1, let's call that I1. The current through R2, let's call that I2. And the current through I3 here, through R3, let's call I3. So right away we should be able to see that I1 plus I2 must equal I3 by Kirchhoff's current law. Well, now let's go and see what we can do as far as analyzing this using Kirchhoff's voltage laws. I'm going to start down here at this corner and make a loop through R1 and R3 and come back to where I started. So I'm going to say that negative 12, I see the negative side of this battery first, plus the voltage drop through R1, well, if V equals IR, that's going to be 8 I1, plus, well, R3, it tells us, is 6 ohms, so that's going to be 6 I3 must be equal to 0. Kirchhoff's voltage law through the left-hand side of this circuit. We can do the same thing on the right-hand side, but now I'm going to start down here, and the first thing I see as I go counterclockwise is the negative side of the battery, so negative 16 volts plus 12 I2 plus 6 I3 brings me back to where I started, so that must be equal to 0. Well, my next step here is if I3 is equal to I1 plus I2, I can plug in, I can replace I3 with I1 plus I2 here. So negative 12 plus 8 I1 plus 6 times I1 plus I2 must equal 0. Or I could rewrite this as negative 12 plus 14 I1 plus 6 I2 equals 0. We can do the same thing over here for this side as well. Negative 16 plus 12 I2 plus 6 times I1 plus I2 equals 0. Or negative 16 plus, now I'll have 18 I2 plus 6 I1 equals 0. Now I'm going to look for a nice easy way to combine these equations. And what I notice over here is I've got 6 I2 here and 18 I2 here. So if I multiply this whole thing by negative 3, both sides, I should be able to add it over here and do some simplification. So if I multiply this whole thing by negative 3, multiplying both sides by negative 3, so I'm keeping that equality, I end up with 36 minus 42 I1 plus negative 18 I2 equals 0. All right, well, what I'm going to do now is I'm going to slide that over here, and I'm going to add these equations together. So if I rewrite this over here, I have 36 minus 42I1 minus 18I2 equals 0. If I add these two equations together, both the left-hand and the right-hand side, I keep that equality. So negative 16 plus 36, that's going to be positive 20. I've got minus 42I1 plus 6I1, so that'll be minus 36I1. And 18I2 and negative 18I2, that's 0. And the right-hand side sum to 0. So effectively, I've eliminated I2. I can now solve this pretty easily. 20 equals 36I1, or I1 equals 20 over 36, which in this case is going to be about 0.556 amps. Once we know I1, it should be pretty easy to go back and find I2 because I can plug this in 0.556 amps right there. So 36 minus 42 times 0.556 minus 18 I2 equals 0. That's just a basic algebraic equation. I can solve that for I2 to determine that I2 is 0.703 amps. Well, great. Now that I've got I1 and I2, I can find I3 because I3 is equal to I1 plus I2. So I3 over here is 0.703 plus 0.556. So I come up with a current from I3 of about 1.26 amps. Excellent. So once I've got that, if I want the power dissipated by R3, well, power through R3, I can use I squared R, which is going to be 1.26 amps squared times R, 6, for a power dissipated of about 9.5 watts. So I've found the current through I3 and the power dissipated by I3 through R3 by using this system of equations. And you can do the algebra any way you want. You don't have to solve it the way I did. But the setup using KCL and KVL is pretty standard. Hopefully that gets you started on basic DC circuit analysis with resistors and voltage sources. If you need more help or looking for more information, check out aplusphysics.com. Thanks, and make it a great day.